Okay, so good afternoon, guys. So this is the final and concluding lecture of the classical mech series that Paul and I have been conducting over the course of these few weeks, right? But then, don't be too happy yet. We will be coming back with much more of these math-heavy and possibly boring lectures. So we'll be doing a series on quantum foundation soon. So get ready for that. Yep.
Yeah.
So let's start off with this lecture. Yeah. So basically, this lecture focuses on three things, right? So the basics of electromagnetic field theory, that's the first one, and relativistic electrodynamics, right? How does relativity come into play with classical field theory? That is the second thing that we're going to look at, and then a derivation for the Lagrangian for field theory, or more specifically, the electromagnetic field, right? Which will be handled by our theoretical physicist with a pen, our great Pugazharasu. Yeah. So naturally, let us kick off things with a review of special relativity, right? So scroll down. Yes, there we are. So note the title, right? It's called Refreshing Special Relativity. It's not an intro to SRES. So at this point, I boldly assume that most of you here know the basics of SR and calculus, right? So this is more of just to brush up your memory. You can also cross-refer to the very famous and the Chinmaya lectures, right? There'll be a link right here. So which talks about immense detail about SR and all the about four vectors and four velocity and everything. Yeah, so definitely give that a check. So yes, but for now we'll be only focusing on very elementary SR, right? Needed for electrodynamics. Right. So if we see the screen here, we see the very famous and very known Lorentz transformations. Yes. So if you're not bored by these equations already, then I can safely say that you're not an undergraduate, right? You're probably a high schooler if you've not seen this, right? So let us get started. So what are these equations right here, right? So you all must have heard about the analogy or the rest frame and the inertial frame thing, right? So if let's take a rest frame and then an inertial frame of reference that's moving at a velocity v, right, with respect to your rest frame. So any object that's, or let's take a line or an object, whatever, in your inertial frame that's moving at a velocity v, it appears contracted, right, because of special relativity. And one more thing to note is there is also time dilation, right? So you got to take that into account. So these set of Lorentz transformation equations essentially relate your initial, right, your transformed or your contracted length, which is x there, and x bar, right, to your initial or your rest, let's say, length, right? So here gamma is 1 by root 1 minus v squared by c squared, and yep, so it's pretty basic stuff, right? So go on. Yes, so four vectors, right? So from here on, this is going to be the language of SR and vectors, right? So four vectors are objects that transform in a predictable way under your Lorentz transformations, right? That we saw in the previous slide before, right? So there is a small term that I'm going to use here called Lorentz covariance, which was what literally I said in the previous line, right? So they transform in a particular way under Lorentz transformation. That's what you call Lorentz covariant. Okay. So they could also be considered to be a group, which comes under group theory, if I'm right. I'm not very adept at this, so I'll be leaving that definition, the more rigorous definition, to Pugazharasu at the end. So if we see it, the x naught component is just Ct, and beta is equal to v by c. Okay. So from that we get your equations, your 6, 7, 8, and 9. Am I audible, everyone?
Yep.
Good. Yep. So yeah, so using your simple index notation, right? So 0, 1, 2, 3. So essentially you construct a vector, right? So that is your 4 vector right here. So go on. This very elementary stuff, nothing to be afraid of. Go on. Down. Yes. So the Lorentz transformation matrix. So we saw our Lorentz transformation equation there. So how is there a way to make it more elegant or to pack that entire set of equations into one matrix? Of course, it is possible, right? So what you see in front of your screen right now is the Lorentz transformation matrix, which is in the center right there. We denote it by lambda with one covariant index and one contravariant index. Essentially, what that means is one mu on the top and one nu at the bottom. Right? So at this point, we don't expect you to go into depth about your covariant and contravariant indices and how they transform, but this is the basics here. So we see on the left here that is our transformed or our contracted 4 vector, right? And essentially what we're doing here is we are just multiplying or we're just operating on your initial 4 vector with your Lorentz transformation matrix, and that gives you your output 4 vector with your transformed coordinates, right? So elegantly we can write it in our summation convention, right? So x bar mu equals summation over nu lambda mu nu x nu, right?
Yeah.
So one thing to note here is that this is a symmetric tensor, right? But we'll look onto that more in details. Go down. There is some sort of symmetry. So proper time and velocity. So what is proper time, right? So proper time is just the how fast your clock runs, right? While traveling on a world line. So what is a world line? So it's just a path taken in SR, right? With reference to your without any reference frame. So what is so cool about proper time is, correct me if I'm wrong here. So it does not depend on the choice of coordinates, right? So what is so useful with that? It is Lorentz invariant, right? So we have one quantity that we can use to measure most of your equations that are going on in your Lorentz transformation equations, right? So d tau equals root 1 minus u squared by c squared. U squared is just your arbitrary velocity. So there's a bit of change in convention here. And eta, right? Eta right here is just ds by d tau. So tau is a proper time. So what is ds here is just your displacement, right? So this is very familiar, right? So displacement by time. So what is that? That is just your velocity, right? So but we don't just call that velocity. We call that 4 velocity because it has your x, it has your eta naught, eta 1, eta 2, and eta 3 components. Okay. So and then in equation 15 we again represent that in your Einstein summation convention. So essentially we're just implying summation here. Again, you can refer to Chinmay's lectures, right, for more detail on this. Next slide. Another very small interlude here, your 4 momentum from 4 velocity. So convention says that what is momentum? P equals mv. Right? So velocity here is your 4 velocity, momentum here is your 4 momentum, and then note that naught at the bottom, right? It's m naught. What is m naught here? It's the rest mass, right? Because we know what happens when mass is accelerated or moving at a great velocity. What happens according to your relativistic equation? It goes equals m squared c power 4 minus p squared c squared. I think. If I'm wrong, correct me. So then, or the more generally known E equals mc squared, where that m naught there is your rest mass, right? So it's important that we use rest mass here and not your relativistic mass, because it will just make your calculations dependent on the frame of reference you're using, and that would throw off your entire purpose of trying to find your 4 momentum, right? Go down. Good. Yeah. So yes, so I'm going to stop here for a moment. So you just take a look here. These are your transformation rules for electrodynamics. I got this from Griffith's Introduction to Electrodynamics, and if you go down, I think around page 480, right, there is a huge derivation for all of this, essentially. But then I'm just going to give you the crux, right? So imagine to derive your electric field component under Lorentz transformations. So what they essentially do is they take two capacitor plates, right? So sigma x and sigma 1 and sigma 2, and they accelerate it to, let's say, in the x direction, and it moves at a velocity v. Okay. So then what essentially happens is the distance between the two plates, right? They change under Lorentz transformation. They change predictably, right? Then what happens when what happens to your electric field when the two plates either converge or diverge? The value for your electric field either increases or decreases. Am I right in saying that? Yeah. So that is how we get our intuitively. There are a lot of equations for the fields and all of that, and then I'm just going to omit that for this lecture. And one thing to note here, I only specifically talked about the electric field here, right, for the capacitors, because for a capacitor there isn't any magnetic field involved, right? So how do you think they could have derived your magnetic field for under Lorentz transformation? Anyone have an idea, Mukund? It's a very simple answer. Hello? Am I audible?
Yeah, you are audible. I think it's more of a connection problem from Mukund's end. He did say he was having like 5,000 ping. So yeah.
Yeah, so I take it that
Yeah.
so I take it that you're not ignoring me, and I'm going to leave that to the benefit of the doubt. So I'm not getting any responses here, so let's go on. So your magnetic field is essentially calculated by using a solenoid, right? And you put the solenoid in velocity v, and then you find out how that one second. So how the velocity of one second.
Yeah.
Just a second. Yep. So sorry for that. There's some disturbance from my side. Yeah. So what happens to the solenoid when it's undergoing Lorentz transformations is that exactly like the length of the solenoid contracts, right? So what happens when the length of the solenoid contracts? Your number of turns per unit length increases, and according to the general laws of electrodynamics, your what's I call it? Yes, your magnetic field also changes, right? Oh god, I'm just getting so many notifications from the other side. It's throwing me off. Yeah, go ahead.
Yeah, next slide.
Yeah, sure. And you can look at that if you want. You can later on just take that. So now let's look at the need, right? The need for something called as a tensor, right? So I'm pretty sure we must have all heard about tensors, but I'm gonna start off by assuming that you don't know what a tensor is, right? So if we go back to the previous slide, we can see that four vectors, right? It's not as simple as just applying the Lorentz transformation to your E or B and then getting out another four vector as your output. But then what happens here is your components of E and B are stirred together, right? They come in one equation or they interchange with each other. So we can't just take a four vector and apply the Lorentz transformation and get your answer and get on with life. You can't do that. So what we need here is we need an object with 6 components, and that is Lorentz covariant, right? So that is the need for an object and a different object rather than just your 4 vector.
Yeah.
Right? And it needs to obey your Lorentz covariant. It needs to be Lorentz covariant. So naturally, if you see the third bullet point there, it needs to obey the rule T dash mu nu is equal to, there are 2 lambdas there, right? One for each index. So you can think of each of them transforming each one of your 4 vector or your index. Okay, so you can scroll down. So this is a very small interlude. So this is the first equation there. The equation 17 is called your symmetric tensor. You can see the symmetry along the diagonal, and it's essentially T mu nu is equal to. So that means the tensor is symmetric, and equation 18 shows you the antisymmetric tensor, right, which is a different one, which essentially means T mu nu is equal to negative of T nu mu. Okay, so just a small interlude there, because just take a good look at this, because we are going to construct our electromagnetic field tensor from equation 18 right there. Right, so go down. This is where the math part comes in, right? So we begin. So how do we construct your tensor, right? How do you construct your electromagnetic field tensor that essentially undergoes Lorentz transformation under a predictable way? You begin by applying the transformation rule to the antisymmetric tensor. But you can cross refer to that if you want later. But then I'm just going to go on. So T bar O1 is just lambda. That's lambda, right? That's capital lambda if I'm right. And there is 0 lambda, lambda 1 sigma, T lambda sigma, right? So if you expand that, which is a very simple expansion, right? So we see here that your your antisymmetric tensor is mostly symmetric, right? And then most of your terms in that cancel out, right? Because it's because of the entire antisymmetry property, right? So if you expand equation 19, you get it in the form of equation 20, right? And this thing right here, since T00 equals T11 is equal to 0, if you go up, you can see that. Yes, so T00 is equal to T11. So yeah, which is just 0 right here. So that was what that entire thing was saying. Go down. Yeah, so using these identities, your equation 20 essentially boils down to your equation number 21, right? It's a huge mouthful saying that out, so I'll just let you read that. And essentially what you did is you just applied your this axiom right there into equation 20, and you got your equation 21, which is brackets gamma squared minus gamma beta whole squared TO1. If you expand that, you will see that you only get TO1, right? So then T bar O1 is just equal to TO1. So we did this for T bar O1. If we do that to your other components, so there are only 6 components here, right? Because of your antisymmetric tensor. So if you do this entire step for each of those 6 components, you get this set of 6 equations right here, okay? Where beta is your V by C, as mentioned in our Lorentz transformation equation. So go down. So yes, so we need a bit of cross-referring here. So Pugal, if you're very fast, just go up a bit. Yes, so take a good look at this. This is going to be a memory challenge. Take a good look at this, and if we go on to our transformation equations for our electromagnetic field, go up. Yes. So this seems awfully, similar to your equations below, right? So what we're doing is we're just comparing these two equations, and if you go down, we get our components for our electromagnetic field tensor, which is really cool, right? So then FO1 is equivalent to EX by C, where your EX, EY, and EZ are just your electric field components in the X, Y, and Z directions, and your BZ, BY, and BX are your magnetic field components along the respective axes. So substituting these values into the antisymmetric tensor, right, gives us this beautiful tensor right here, which is called the electromagnetic field tensor, right? So the significance of this electromagnetic field tensor is very vast, right? So essentially what this entire tensor did was it encapsulated everything, all of your variables of your electromagnetism and everything, and Maxwell's equations. It just packaged it into this beautiful Faraday tensor, right? So yeah, go down, and there is also, and then yeah, here we are gonna see this is called the dual tensor, right? Don't take this too seriously right now, because the use of this isn't gonna be explicitly derived in this lecture, but then I'm just putting this here just for the completeness, right? So the dual tensor is obtained from the electromagnetic field tensor by using a substitution. E by C is becomes B, and B becomes E by C to give you this equation 23, right? So the dual tensor and your Faraday tensor is essentially used to derive your Maxwell's equations, right? Instead of all your huge cross products and all of that, you just package it into one tensor, and then you can just derive it directly from this, right? Yeah, we'll go down. So yeah, this is just a small review. You can just have a look at this. These are the very familiar Maxwell's equations. I'm just putting it here because Pugel later on will be deriving some of these from Lagrangian, right, for your electromagnetic field tensor. So I don't need to tell you that, the equation 25 is your Gauss's law, and 26 is your Faraday's law, and 27 is your Ampere's circuital law with the correction, right? So yeah, this is pretty familiar, right? So go down. So again, this is another talk that I think Pugel has done before about gauge symmetry and gauge fields. I was not there, but I think you can take a look at that for a much more detailed explanation on this topic. But then I'm just gonna very vaguely tell you what a gauge field and a gauge invariance is. Right. So from Gauss's law directly we can derive equation number 28, right? So B vector is just your nabla cross A vector, right? So what is this A is our question here, right? So if we rewrite this equation number 28 in terms of scalar and vector potentials, and as again a small interlude here, we can either represent our electromagnetism in terms of fields as in E or B, or we can represent them as potentials, right? So either for ease of calculations or ease of notation, we can interchange between the both. So then your scalar and vector potentials, if we rewrite this equation number 28, we get our equation number 29, right? So we get E plus dou A by dou T equals negative nabla phi, where your phi is your scalar potential, right? And I think A there is your vector potential.
Yep.
Yep. So equation number 30, right, gives you a very cool invariance, right? So if we make a small change in your A, we don't know what A is yet, okay? If we make a small change in A as A vector plus nabla lambda, right? And we choose our vector potential, your scalar potential according to this equation number 30, we can make a change in A right here so that your magnetic field or your electric field doesn't change, right? So what do we call this? This is what we call as your gauge invariance, right? So you can make a small change in your gauge field A, and then that will not directly contribute to a change in your magnetic or electric fields. So go down. Yes. So these are some examples of your valid gauges. There is not a huge number of gauges that satisfy equation number 30 and 31, because you need to choose them carefully so that it doesn't change your magnetic fields, right? So then equation number 32 is very popularly called the Coulomb's gauge. So I'm not going to be proving this here because it's a pretty tiring job to substitute this into these equations and see what results you get. But then this is just for your own reference. And there are also some relativistically invariant gauges, right? called the Lorentz gauge. I think we looked at the Lorentz gauge in Chinmaya's first lecture, right? Where he very slightly or neatly just introduced us to dou mu a mu of x equals 0, and then he constructed the Lagrangian and all of that from that. Right? And then equation number 35 is called your relativistic Poincare gauge, right? Again, I'm not gonna say that you need to learn this or you need to know this. I'm just leaving this here to like give some intuition of the examples of the valid gauges that are present in nature, right?
Yeah.
So then I think I'll hand this over. So a quick note here is that what is a gauge field? You can define your gauge field as something that your Lagrangian, right, is invariant in that field, right? So then I think Pugel will take on from that. He will derive the Lagrangian, the Lagrangian for that electromagnetic field tensor that we saw above. And Pugel, talk to you.
All right. So
second.
Rishi. Yes, Mukund.
So in the equation 33, what is the n here? The non-relativistic axial gauge?
We'll get back to that at the end, I guess. So we'll post the questions at the end. Yeah.
I'll start with just recollecting the basics of Lagrangian mechanics. Well, we have this scalar called the Lagrangian, which is defined as the difference between the kinetic energy and the potential energy. And here's the deal. Okay, if I have a system that's described this way, the path taken by that system is sort of given by this integral when it's equal to 0. Right? So this gives me the path of the integral. of the system. This is often dubbed the principle of least action, when it's just the principle of extrema, in my opinion. Because again, it doesn't need to be, the saddle point can be either way, right? When you consider this go to 0, can be either a minima or a maximum. So that's how I would say. A principle of extremums, Next thing about the Lagrangian is that if you want to extract the equation of motion from this Lagrangian, the equation of motion would just be, for the entire system, that is, would just be something along these lines. And this is called the Euler-Lagrange equation, and this is the equation of motion. And this is often, as I said, it's called the Euler-Lagrange Euler-Lagrange equation, and it's quite easy to generalize this for more than one degrees of freedom. So here my only degree of freedom is x, but I could also then say, okay, x is just a subset of some x0, x1, and x2 and so on, and I can sort of denote them as xi. But the common convention is to denote it as qi. And basically, if you substitute this, you would just get. Obviously, there's a summation sign in front. We're just ignoring it due to Einstein notation. If you want to write it out, it would just be like this. The summation sign would be there, and it would be the same summation sign on both sides, which is why we don't really bother, because we understand that if there's an index like this, obviously, there's going to be a summation sign. And yes, so this is how you would write it for a general set of coordinates qi. And oftentimes in convention, people have a tendency to replace this with pi. This is called generalized momentum or canonical momentum. Okay, so if you then sort of replace this in the equation, this would then imply dou L by dou Qi is equal to Pi dot. This is yet again the same Euler-Lagrange equation expressed in a different language. I'll just sort of highlight this because this is because this is kind of the form that we will be using, right? So just to sort of, this is very, very important, or I just put important. Yeah. Now what we'll do is we'll look at what happens in field theories, because here this case only applies to particles. What happens in field theories? Well, your Qi here has to be replaced with a more general function that spreads across all of space and time. So this is a field in a very loose sense. Another thing which you may not have noticed is the Lagrangian is actually defined quite rigorously as a map that takes the generalized position and that takes the generalized position of velocity, or Qi dot, time, and it's a map that takes this set to a real number. So you have a Qi dot dependence here as well for a Lagrangian. So, then your Qi dot would then become something else. It would become a more generalized, I'll explain this in a moment, difference. Because here you've got space and time components. That's why I'm using this 4 gradient. This 4 gradient is a generalization of the 3 gradient or nabla that we often have been exposed to, which is written as follows: 1 by C dou over dou T, comma, the nabla. So this is essentially what the 4 gradient is. Again, this is the slight probable thing, which is, this is the covariant 4 gradient. And if you want to get the upper index version, which is the contravariant 4 gradient, you just have to multiply this by the Minkowski metric, which I'll get to as well. But essentially, what you need to know now is we're sort of transforming our localized position and velocity to something that's sort of spread out over the field. So my Lagrangian, essentially, I would just minimize this guy right here. But then this guy is spread out over all space. So I would have to minimize something else. I would have to minimize this integral. And since it's spread out all over space, is why I have d3 of x, where d3 of x is just sometimes written as dv, the volume element. And I'll also have to integrate with dt. Well, we usually write a very fancy L here. That's called the Lagrangian density, because I have to integrate over all space and time. And a shorthand way of writing this would just be Lagrangian density integrated over all 4 degrees, which is 3 degrees of space and then 1 dimension of time. Okay, so this is, and we will write this Lagrangian, this Lagrangian density is what we care about, is written once again as the potential energy minus kinetic energy, but it's written, the Euler-Lagrange equation, however, changes. So how does the Euler-Lagrange equation change? So your L is dependent on phi, not on Q, so it would be dou L by dou phi I, which is equal to dou by dou Y. Why is it dou by dou Y? Because that's my, dou by dou X I would say, because your phi is sort of dependent on your I. Of, again, here's where it kind of gets tricky, of the Lagrangian with respect to, this is where it gets really, really, really messy. The derivative of this with respect to the derivative of phi with respect to xi. The reason is because, and this is essentially just the phi with respect to xi is essentially just this 4 gradient. So, whoops. So I could then rewrite this as follows. So dou L by dou I dou Y phi. So this is because we are generalizing to field rather than a singular particle. And this equation will sort of help us out when we're talking about the electromagnetic Lagrangian. All right. And there are 5 or 3 steps which we'll go through. So before we even start, we need to construct 4 vectors. And the reason we need to construct 4 vectors, you ask why? And the reason is simply because they are Lorentz covariant. And this, basically makes them compatible with special relativity. That's why we care about them being Lorentz covariant. So the objects that we've encountered so far, so we've encountered a few objects that are related to quote unquote sources. Sources of what, you may ask? Sources of charge and current. Okay. So what and all have we encountered? We've encountered rho, which is the charge density, and then we've encountered current density J, which is a vector. And these are the two sources. And then obviously there's a source of the field, which we encountered as a vector, which is the vector potential, and phi, which is the scalar potential. Right. So now what I want to do is I want to write them up as 4 vectors, and you can quite clearly see that these are sources for the fields. These are, these are sources, and this is the field. So I will group them accordingly. And the easiest way to group them is as follows. So I will now define a new object, J mu, and it is defined as C rho comma J vector. So I'll tell you exactly why this is useful in a moment. But for now, we're just trying to construct 4 vectors, and the definition for 4 vectors, if I should remind you all, is very simple. The definition is that if I take a Lorentz matrix, and if I act on a 4 vector J mu type mu, well, what am I doing here? I'm just trying to find, this is like finding the length, because I'm just taking this guy and I'm multiplying it by the dual, which means I'm just trying to find the length of the elements inside J. And this Lorentz transformation is an orthogonal transformation, which would also mean it's an isometry. And isometry is this very, very, very fancy word for saying distance and angles preserved. That's all that matters. So, well, since I said distance preserved, that would just mean, there would be no change. This would just be this. And in fact, there's a defining equation for the entire Lorentz quote-unquote group, which is the collection of all Lorentz matrices. It's like Lorentz matrix belongs to the Lorentz group. Well, the defining equation for a Lorentz transformation is essentially just this guy right here. And neta is not your 4 velocity. Neta, on the other hand, is what is called the metric. And metric is just this right here. So in the diagonal, I'm not writing the zeros, but you get the picture, right? And sometimes it's also equivocated to, the plus minus as well. Both of them mean the same thing when you're trying to calculate the length. But at the end of the day, this is what neta means in the context of field theory. And this is called the Minkowski metric. It helps us, compute angles and length in spacetime. So this is the Minkowski metric, right? So this is the definition of a 4 vector. So we'll probably put it up as what's a 4 vector. That when you're referring to this, it would be useful. Yes. Anyways, coming back here, the second object that I will construct is the mu. And again, I'm just going to combine it, and I'm going to put the scalar first instead of the vector. So it's going to be a little different this time. It's going to be something like all right. So along with this, I'd just like to remind you that we did define another 4 vector, which is the 4 gradient, defined as 1 by c dou by dou t, blah, blah. Right? As you can see, we're taking a very pragmatic approach. I don't want to sit and prove that this is a 4 vector, and this is a 4 vector, this is a 4 vector. You can pretty much just shove it into this equation and see that, it is isometric at the end of the day. So yes, so with these three in mind, these are our very important objects for electromagnetism. With these three in mind, let's move on to construct the Lagrangian. And this is how we're going to think, right? So we're going to think in terms of in terms of satisfying these 5 conditions. And let's go over the conditions first. Okay, so the first condition is Lorentz covariance, which as Rishi explained and I just outlined, which is to say that, if I act on the length with the Lorentz transform, it is supposed to leave that 4 vector unchanged. Or if I go from one frame to another using the Lorentz transform with that 4 vector, it transforms in a very, very predictable way. And the second thing I want is a conservation law. And the conservation law that I would actually consider in this case, the conservation principle is nothing but the continuity equation, right? And I'll explain that as well. But essentially, I want my Lagrangian to satisfy these 3 physical conditions, which is Lorentz covariance basically means all inertial frames are valid. I can look at my system using any inertial. Conservation laws basically means there's charge conservation at the end of the day. And gauge invariance means gauge invariance is a rather more abstract thing to think about in terms of electromagnetism at least. And all gauge invariance is telling me here is I can sort of shift my gauge whichever way I want to. I can change my A provided, it's just a differential. I can shift my entire global viewpoint however I would like to. So yeah. So these are my physical, conditions. The first 3 are quote unquote physical. They are properties of the theory, and I need that to be true. And the other 2 are more implicit. They are of the mathematical machinery. The Lagrangian must be a real number, or it must be a real valued function at the end of the day. And my Euler-Lagrange equations should be equal to my Maxwell's equations. Because like I defined earlier, if I take the Lagrangian and pop out the Euler-Lagrange differential equations, they are the equations of motion. And the equations of motion for electromagnetism are Maxwell's equations. So we're going to try to do that from, at the tensor that we saw earlier. And we'll also see how the tensor is constructed. So first, let's go for Lorentz covariance. And, to satisfy Lorentz covariance is a very rather simple thing. So we want to make our theory, quote unquote, manifestly Lorentz covariant, which means it is a part of the building blocks of our theory. And the easiest way for Lorentz covariance to be manifestly present in our theory is just to use 4 vectors. That's our solution. So we are going to only use 4 vectors and objects formed which follow the same or more predictable transformation laws as those 4 vectors themselves. So that's what we're going to do to sort out Lorentz covariance. Now, what will I do for my conservation law? Well, the simplest conservation principle is nothing but the continuity equation, as I explained earlier. Right? So let me just get it. So yes, I just want my continuity equation, and it is basically you take the divergence of j, it's equal to 0. You take the derivative of rho, it's equal to 0. So that's all that there is in the conservation law. So I just want conservation charge. Well, how would I go about doing it? Well, I have my j mu here. And what if I do the 4 gradient on j mu? Just a reminder, the 4 gradient was 1 by c dou by dou t and the nabla. And this guy is acting on my c rho comma j. Okay, so this is what is happening. If you just go component wise, it's quite simple to see that dou rho by dou t plus dou g dot is this is it. This is the continuity equation that we were seeking, and all of conservation of charge is just present right here, because we know that if you consider what this guy is telling us is, you consider a small enough portion where the flux lines cross, there is no net outward flow of charge, because whatever comes in, that's all that goes out. So there's no net outward flow. And also there's a correspondence, which is to say that as my charge increases or decreases, increases over time, my net outward flow would decrease, because that would mean more flux lines entering, right? So this is with respect to a charge sort of emanating field lines, think of it that way, and this is with respect to flux and how it's sort of. So when you add these two together, you zero. And again, voila, I've sort of ticked off two of my steps here. So I've got Lorentz covariance, because I'm going to just use 4 vectors all the time. This is a promise I make. And conservation laws, I can get that just out of this one simple equation. Yes. And now we will try to do gauge invariance. But before we even go to gauge invariance, I would like to construct the electromagnetic field tensor. Right. So the way I would construct it is by saying f mu nu is equal to dou mu. Whoops, let's go for the covariant part first. F mu nu is equal to dou mu, a mu, a nu minus dou mu, a mu. So fear not, I am just summing. There's like a small summation over here. We just haven't mentioned it. So summation with respect to mu and nu, or you can think of it as, what's this component telling me? And I just substitute. If I want to find the 0th component, I just substitute 0, 0, 0, and then I just get something here. So I am claiming that this is the, let me take this off because I want to stay on track. I'm saying that this is the Faraday tensor. Well, how do I know? Well, two properties that we saw of the Faraday tensor, just to sort of flashback, was, hey, it's traceless in the sense that it's all of its diagonals are 0. So if I take the sum of its diagonals, which is the trace of it, it is 0. And f mu nu is equal to minus f mu mu. So I just write out those two properties here. So we have two things to prove, or prove that the trace of f mu mu 0. This is first proof thing I need to prove, and then the second thing I need to prove is that f mu mu is equal to minus f mu mu. Well, it's quite obvious when it's written in this form instead of the matrix notation. So how would I say it's obvious? So let's just substitute all zeros for f mu and nu. You just substitute zeros, it's just dou 0, which is dou by dou t, or acting on a, which is just the rho, right? So if I, for example, I'm just going to take example. If I do, I'm going to solve one first. So I just want to find out f0, 0, which is just dou 0, a0 minus dou 0, a0. Well, I don't even need to do any substitution. All of this is just 0. And if I do this for f11, f22, f33, all of it's going to be 0. So, I've kind of proved this. It's done. It's sorted. And to prove the other one, I'll just find out what f mu mu is. What is f mu mu? Which that would just be dou mu a mu minus dou mu a mu. It looks oddly similar to this guy. So if I just take the minus outside, it would just become dou mu a mu minus dou mu a mu. And this is essentially just the untransposed tensor itself. So you swap the indices, you get the negative guy. So this is anti-symmetric. Yes. But does this show gauge invariance? So that is the question that we must ask. And that is a question that has a fitting up. So gauge invariance is what we'll prove now. So I'll just make a small transformation. A mu going to A mu to mu F for all, this is for all F which are content. And I'll explain why we're making this assumption. So I make this change in my definition of F mu, and I'm just going to sort of do mu A. So, it's A mu, but it's A mu plus do mu F minus guy right here. And if I just write this out, it would just become do mu A mu plus do mu there would be a minus here as well. Yeah. So now, this term and this term is essentially just F mu nu. This would be F mu nu prime because of the transformation, but this would just be F mu nu plus do mu F minus do mu F. Well, if F is a continuous function, which is to just say no holes in the field in which it inhabits or the field in which it produces, scalar or vector field, it doesn't matter. That means the ordering of the partial derivatives doesn't really matter. It would just give me the same result. So this would just go to 0, and I would just get F mu nu back again. So F prime mu nu is just the same as F mu nu. Hence, this is indeed a gauge transformation, and this is also displaying gauge invariance, I would say, because when I transformed the potential, when I made a small displacement of the potential, it didn't change the structure of the Faraday tensor. So this Faraday tensor is a very interesting object because we set 5 conditions for a Lagrangian, and it seemingly followed 3 of them already. So, so the easiest solution for the Lagrangian would then be to use the Faraday tensor itself, because 3 of these conditions that we were looking at are already manifest in the Faraday tensor itself. Right? Give me a second. Let me just fetch some water. All right, cool. Now, how would we go about constructing the Lagrangian? I seem to have gone out of slides. Whoops. Let me just see. Opening some. Let me just try to add a empty page over here. Yeah, cool. So to double check something. Yeah, okay. So I'm going to use this space to construct my Lagrangian. So I need my Lagrangian to be, first of all, a real number. And if you look at the Faraday tensor, the most easiest way is to say that, hey, if I take the square of this component and then add it with this component, that's obviously going to be a real number. Nobody uses complex components, right? So, well, that's the easiest way to do that. So the naivest approach to a Lagrangian would just involve a scalar based on just the approach that hey, it needs to be a scalar, and I will use the Faraday tensor because as you've seen, it's just manifest. Here's the thing: this product, it is going to be a real number, so we are valid, and it does have all of the three conditions manifested in it. But what are we sort of missing here? What do you guys think we're missing? Well, to answer the question, we are missing our sources. We do not have a J or an A here because those represent our sources and we need them in our Lagrangian. Otherwise, we're not talking about an interaction picture. We're not talking about where the sources interact with the field or with each other. So again, the most naivest way to include them would just be J mu, A mu. All right. Apart from this, there are a few factors that are okay. So another analogy-based way to think of this is the kinetic energy, where this is the potential energy, and you would have a minus sign. Yes, this minus sign could be thought of that way, but when we're actually doing the EL equations, when we're trying to derive the Euler-Lagrange equation for Lagrangian, you will actually find out that this minus sign has a role to play. Also, another factor that's commonly added is this factor, where mu is just the commutivity. The commutivity, yes. And obviously, you might have also noticed that there's no C or there's no epsilon naught. There's only just the mu naught. There's a very interesting relationship between all the three that we get from the wave equation. So whenever we want to go from two of them to the third one, we can just sort of use this relationship. All right. So yeah. I'll explain the 1/4 as well. So our Euler-Lagrange equation for electromagnetism is written as follows. This is...
Hello. Oh yeah, we were unable to hear you in the middle.
Where were you? Like, which part were you unable to hear me?
Oh, only 15 seconds.
Okay. So I'll just explain this one more time. Well, I'm just trying to get the Euler-Lagrange equation for using this Lagrangian, and all I'm doing is I'm using the field theory Lagrangian. Right? And it's just differentiated with respect to this right here. It's the rate of change of this guy. All right. So yes, this is quite trivial. You do the differentiation of this, I would just end up with minus J mu. However, what's not so trivial is this end of the equation. It does involve a lot of tensor identities and things of that kind, so I don't want to go too much into it. But you guys, I will sort of link up in the description, a place where you can see how we get this. So essentially, the reason I added a 1/4 is because there is a factor of 4 that you would get times 4 due to this mess that we have here. And that would just sort of cancel out because we just don't want to have some 4 floating around. And as you know, the physicist's tendency to be lazy or much neater would just sort of setting things going to 1, similar to what we do with natural units. So essentially what I'll get in the RHS is I'll get minus 1 by mu naught times, I would get dou mu and I can just cancel out the minuses and I can rewrite this as follows. So yes, this is it does contain all of our Maxwell equations. It really does. It's quite surprising that all we did was we obeyed the 5 laws, and we got these principles, and we did this. And I'm saying to you guys right now that this contains the Maxwell equation. Well, let me show you an example. Right. So if I take, for example, tau mu of 0, this would just mean I would have to take dou 0 f 00 plus dou 1 f 10 dou 2 f 20 plus dou 3 f 30. Now, if you recall from the definition of the Faraday tensor, this goes to 0. However, these terms survive, and the first derivatives is dou by dou x, this is dou by dou y, dou by dou z. And if you refer to the Faraday tensor back again, you will see that these are all the f's here are just components of the electric field. So I'll get something like this. I'll get dou by ex, e x up here plus dou by ey dou by z. Yeah. And this pretty much just looks like divergence of our electric field, right? Component-wise. And what do I have on the RHS? I have this should be dou nu, not dou mu. Should definitely be dou mu. And I have set this conveniently to 0. And if I set this to, and I have I cross multiply this, so I get my mu naught here. So I had basically, in the RHS, I had mu naught J0, which is just mu naught times T rho. And there's been a mistake somewhere, but essentially, if you do some canceling out, you would see that this is Gauss's law at the end of the day. And similarly, if you sub in the for one index side, it's for 0, you do for 1, you do for 2, you do for 3, you'll get all 4 of Maxwell's equations. So, instead of using vector identities, instead of using a lot of vector calculus and making physical considerations, we made 3 physical considerations, which were pretty abstract, to be honest. And 2 considerations on what or how our Lagrangian should be. We just had 5 steps, and we neatly arrived here. Well, yes. So this is a true description of Maxwell's equations in vacuum, without any sort of matter, whatever particles floating around. Of course, there's a small thing. So what we would generally, this Lagrangian can be broken up into Lagrangian field. As you saw, the f mu nu is that exactly, plus the Lagrangian of interaction. But if you notice in the Lagrangian of interaction, you did not have certain coupling constants that we often talk about in high school, at least. And the coupling constants are your electric charge and the mass of your electron, right? So one thing you should keep in mind, this is not a quantum description of charge. This is not how we're thinking. We're thinking at a very classical level. So when you go to quantum electrodynamics, this entire term would change. So that's pointer number 1. And pointer number 2 that I would sort of I would say is that, is this the only Lagrangian that you can construct? Hell no. There are various other Lagrangians, expressed in different ways in textbooks. But, I would say not too many of them exist, or, they are heavily constrained centrally because of our conditions that we impose. You want Lorentz covariance and the conservation law and the age invariance in a single theory. Well, it's you're not going to have many theories that consistently follow all of them. And to construct a theory, the most easiest way is what we've seen so far, is just to use 4 vectors, play around with them, construct a new tensor, play around with it, using the the Lagrangian formalism, and at voila, you get your Maxwell's equations nearly out of thin air. There's nothing really too magical about this, but what it is it's very compact. It's very how do you say? It's very explicit. Our conservation laws, our symmetries, our considerations are very explicit in this formalism. And the mathematics behind this is also very rigorous. There's no loose ends. We do not have to reach out to thinking about singular vectors because we now know how a 4-vector by itself would transform. I don't need to think about singular components. That sort of thinking is completely gone away with this approach. And I hope this was an interesting way of thinking and arriving at familiar results that we've all seen on our classrooms. And with this note, I would sort of conclude and open the room for any questions. Thank you.